We are ready to restart. Do you hear me?
Yes.
Thank you. We have seen the max removal transformation as one of the canonical tricks used in OPF simplifications. Let's test it on this little example. Here I have a problem. Minimize the absolute value of x minus y minus 5 over linear constraint inequalities and linear inequalities here. Here I have two candidates simplifications of rewritings of the problem that try to make it a linear problem. Minimum t, so the objective function is linear, and I have a number of inequalities that are all linear. Is any of those a correct rewriting of problem P? I close the poll in a few seconds. The majority says A, which is the correct answer. Of course, B is incorrect, because if you minimize T, and the only constraint you have of T are those inequality constraints, and for any X and Y that are fixed here in this set, so if this set is non-empty, I can fix X and Y, and then I have limits on T, which are only upper bounds. So if I want to minimize T, then the minimum is minus infinity. So that is obviously wrong. The only question that remains is whether A is correct. And the answer is yes, because the trick is to, know that absolute value of a number is the max between this number and minus this number. So the objective function can be written as a maximum of two linear functions, this and its opposite, which leads to minimize T, where T is larger than the first element of the max and the second element of the max. So this is a well-known trick. If you didn't know it, now you do, and you are now well equipped to solve a large number of problems, because using piecewise linear approximations of convex functions is some technique that is quite commonly used everywhere in the kind of problem we will see. Indeed, the kind of problems we're concerned with, the AC OPF problem, is unfortunately, or fortunately for researchers, it gives a lot of work to do and justifies courses like we're doing now, is non-convex here. It's non-convex because the set of feasible variables is non-convex because of the equations of AC grids. Of course, you could make it non-convex because you have an objective function that is non-convex, but even if you make everything in the objective simple, even linear, then we will have non-convexity due to the grid constraints. Here is a concrete example here. Here, I'm trying to look at what are all the possible feasible injections in this small grid. Here I have a grid with two nodes. One is the slack bus, or the reference bus here. Another one is a bus where I have an injection of power, which is positive or negative, so I can consume or produce here. The line admittance is given by this here. There's no longitudinal component, but transversal components, but the longitudinal components are given here. And I assume the only constraint I have are the voltage magnitude at bus 2. The voltage at 1 is the reference. At bus 2, the magnitude should be between plus or minus 5%. Here is all the possible injections that we have for P and Q. So in red are the possible values here. So we see this is a non-convex area, and worse, it has those 2 points here. So for example, if I take a linear combination of P, if I want to, for example, maximize P, if I'm operating in this region, I will have a local maximum, which is here. If I'm operating in this region, I will have another local maximum that is here. So this has local maximum of a linear function of the power, for example, so that will clearly not be an exact convex problem. So that's the nature of the AC OPF. So what we will do in the rest is to do approximations to try to live with this simplicity. There is a question here, Pierre Tarazi.
Yes, I have a question about the quiz, the last one.
This one?
The quiz, yeah.
This one?
Yeah. You were saying max, we had min. I don't get it.
You mean the max?
Here it was you want to minimize the function.
To minimize a function, and this function is a maximum of two functions.
Okay, so I think this is the part I do not understand. How is it a maximum? I don't get it.
Well, that's the theorem we saw here. If I minimize an objective function, here, forget about all the other ones, take only f1. If I want to minimize f1, so I want to minimize this thing here. And this thing is itself a maximum of linear function. The intuition is the following. If you plot linear functions, and if you take their max, you obtain a convex function. Here I'm plotting a number of straight lines. I take the max of them. I obtain the black line. I apologize for it's not a perfect black line, but if I take the max of a number of linear functions, I obtain a convex function. If I minimize a convex function, I have a convex problem. That's what I want to have. So if I have a convex function that is given by a max of things, I can ignore the max, which is ugly to use. There is no differentiation that you can do. You cannot really work with max in an objective function, but you can remove the max from the objective by replacing the function that had a max in it by an optimization variable, and add the constraint that this optimization variable should be larger than all of the components. So what we did here is exactly the same thing here. I had to minimize a function which is the max. It is the max of two things. It is the max of x minus 1 minus y minus 5 and minus x plus y plus 5 plus the constraints here. So that was my original problem. That's the problem B here. And what we are saying is that in order to solve this, what you can do is replace the max by an additional variable t and add the constraints that t must be larger than x minus this, and t must be larger than minus x plus y plus 5, and the other constraints, and that is exactly the formulation A that we have here. Does it answer your question?
Yeah, thank you.
You're welcome. And again, that's very important because, as I have perhaps tried to illustrate here, whenever you have, for example, a square function, like the black function could be taken as an approximation of a smooth function that could be a quadratic function. So we can replace things that are quadratic and complicated as long as they are convex by taking linear approximation. And those linear approximations, if the function is convex, will become a max of linear things. And this max of linear things, we have now a technique to remove them entirely and transform our problem that was originally a convex problem into a linear problem. So that's one of the topics. And it will be important to be able to recognize this. So because MATLAB will not solve for us problems that have max in them. Nonetheless, of course, the OPF problem is non-convex, so with those techniques will not be sufficient. So let's see additional techniques. We will see two linear approximation techniques of the AC OPF. One that is very brutal, but very important because it gives a lot of intuition on how the grid works. It's called a DC approximation of OPF. A bit later, we'll see another approximation that is more subtle. That's the local linearization, but it's which is more subtle and finer, but is not global and does not give such a good intuition about the grid as the DC approximation. The DC approximation of OPF, as I said, is very brutal, so should not be taken seriously if you have to do voltage control in your grid, for example, but gives a first-order approximation when some assumptions are true. And those assumptions are those following three ones here. The resistance of the lines is small compared to the imaginary components, so the conductance, which is true in many AC networks where you expect them to operate in regions where the resistance is small compared to the currents, so that the losses are small here, but the reactance, which are the inductive components, sometimes the capacitive components when you have underground cables, cannot be neglected. It's impossible to remove them entirely. So that's one hypothesis that is true traditionally in transmission networks. So DC approximation is done, for example, to do a first pass on the electricity market where we model the continental European grid using the DC approximation. At this level, it is fairly good here. Also, two additional assumptions: that the grid is operating in a regime which is close to nominal values, meaning the voltage magnitudes are close to 1. Of course, this is not always true. If the grid is collapsing, your voltage will perhaps be 50%, but then when that happens, typically your grid will not survive very long. So that's not the steady state. So that's assumption is done. And the voltage angles are small because also here, as we have seen, the voltage angle differences are proportional to the power flows. And given the values that we find in inductances on lines, the voltage angles must be small. Otherwise, typically the power flows are huge and something is probably not working in your grid. So those are steady state assumptions for high voltage grids here. This is a model of a line that you've probably seen in the previous module. So we can model a line with a longitudinal impedance and shunt impedance here. I'm giving here all the notation for those various elements. If I have a line that goes from bus K to bus L here, the complex power that's injected at this end of the line here is given by this formula. The one that flows into, not the one that's injected, that's yes, the one that's injected at the bus here is given by this formula here, which as usual is given by the product of the complex voltage and of the conjugate of the complex current. We can expand this and by exposing the various components of the impedance matrix that is given here. And in the DC approximation, we are interested only in active power. So the DC approximation entirely ignores reactive power. So it cannot be used for voltage control. We use other techniques. So the DC approximation considers only active powers here. So if I want active power, I take the real part of this, and then I will do approximations that are consistent with what I said before. I will set the resistance part of the line to 0. I will set the voltage magnitude to 1. And as I think that the voltage angles are small, I will do the approximation of the sine by sine theta is equal to theta, and cosine theta is equal to 0, because cosine theta around 0 is order 2. So another way to put it is that the first order development of an exponential, complex exponential here is 1 plus j theta here. So if I use those approximations.
There's a question on the chat. Oh, okay. Yeah. Okay.
So there's a question on the chat. Why does the first what does the first approximation of the DC approximation mean? So the first approximation, resistance 0. That's the question, right?
Yeah, I was confused about just the written expression of the resistance and the conductance, but I just realized that yeah, susceptance is greater than conductance in this case.
Yes.
When yeah, okay.
Good. So if we do those approximations, we expand here by writing the complex voltage that was written before as complex numbers. I write it now in polar coordinates with the magnitude and the phase angle. The magnitude is set to 1, and the complex exponential is replaced by this linear complex expression. And at the end, we take only the real part because we're interested in the active power. So we obtain this expression, minus BKL, the angle difference, and minus BKA, which is typically, BK is typically negative, minus BK is the imaginary part of the nodal admittance matrix elements that we find at position KL, that is typically called capital BKL, which is typically positive, not always, depends on the grid, but in many grids it is. And this gives this approximation, which is exactly capturing what I mentioned on the example before. It says that the power from K to L is proportional to the difference of phase angles from K to L here, and the proportionality coefficient is exactly BKL. So that is the first element of the DC approximation. Second, so if I, for example, I'm interested into the power injected at a node, then the power injected at a node, the active power is the sum of the power flowing on the lines. So we'll have, by simply summing up all the equations I had before, I will have this equation. So that's a simplified electrical grid modeling where the state of the grid is only the angle here, because the complex voltage has magnitude 1. And then we have the active power injections given by this linear relationship. Furthermore, because the DC approximation ignores power losses, the resistance are 0, then the sum of active powers in a grid is 0. Of course, this is an optimistic assumption. We have seen that in the previous example of a grid, when we were looking at the results of the MATLAB exact solution of the OPF, we saw that there were a few % of losses. So the DC approximation ignores the losses. An important thing to remember. So when we use the DC approximation to close markets in at continental level of Europe, for example, we first do a DC approximation, we allocate all the power flows, but then we must do an allocation of losses, because when we do the real stuff, there will be a few % of losses. So this is typically requiring an additional step after the optimization based on DC approximation. So let's apply this to the toy example we had a minute ago. That's again the same example as before. Yes, question? No, no question.
Sorry, my mic was on.
So let's redo the modeling of the grid we had before. Before we had a modeling of the grid where the electrical state was the complex voltage. From the complex voltage, we could deduce all the derived quantities like the complex currents, the complex apparent powers in the lines, the apparent powers in the line, and also the complex power injections are all the nodes. Here we will do the same thing, but everything will be simpler. First, there is no reactive power. With the DC approximation, we look only at active power. And here's the first equation we have at node 1. At node 1, the injected active power, P1, is given by this formula that is derived from the impedances of the lines here. We take only the imaginary part here, and we obtain, so the minus B, which gives a plus 22.2 per unit. That gives this for the power flow from 1 to 2, theta 1 minus theta 2 times the B element of the line. This element here is from what is flowing from line 1 to line 3. Same equation at node 2, same equation at node 3. And I write also the power balance. The sum of the p's must be equal to 0 here. Now, we need to solve for example, if I want to do a load flow, I want to know what is the power flowing everywhere given the, if I want to know what is the state of the grid, which are the angles given the power injections, then we need to solve for thetas here. Of course, there are 4 equations and 3 thetas, but in reality, we have only 3 equations, because you will quickly see that if you sum up the first 3 equations, you will find P1 plus P2 plus P3, that is equal to 0, and the sum of this will also be 0. So one of the equations here is redundant. This last equation is unnecessary if we have the 3 ones. That's the first thing. Second thing, we must still have a slack bus. We must have a reference bus somewhere. So the reference bus will have complex voltage equal to 1, which means magnitude 1, but we're assuming magnitude 1 everywhere anyhow. So we will need simply theta 1 equal to 0. So this boils down to something simpler here. We need to set theta 1 to 0. And the branch flows, the flows on every branch, will be derived from the theta using the DC formula, equation 0 we saw a minute ago. Of course, here we're not able to compute the line current because we've lost the reactive part. So we're only able to compute the power that flows. This is why very often we give apparent power limits, or that are even interpreted here as active power limits, when we do only the DC approximation. That's the only thing we're able to do.
There's a question.
Why do you take minus BKL? Well, because this is the question is, why do you take minus BKL? Well, because this is what the power the DC approximation gives, right? It gives minus BKL here when you do all the maths. BKL is typically negative, so minus BKL will typically be positive.
There's a second question, I think.
So the question is, are you taking into account line losses? Well, the answer is no. In DC-OPF, we ignore line losses. We assume that the power, we look at only at reactive powers, and we ignore line losses, as I mentioned already. So that's, of course, a limitation that we need to remember when we do, when we run a network with the DC-OPF. The DC-OPF cannot be used to compute line losses, for example, or not even voltages, because it sets the voltages to 1. Those 2 things are ignored. Voltage problems are ignored, line losses are ignored. So DC-OPF is an optimistic thing that ignores all the problems. But nonetheless, it is useless because it captures where powers are flowing. At first order, what is the goal of a transmission grid? It is to transmit active power. So where does power flow? Is power flowing now from Germany to Italy, or the other way around? That's the kind of things you want to know when you control the European grid, for example. You do this with a DC-OPF because that will give you answers to such questions. It will not give you answers to questions such as, how should I control my voltage problems? What should be the set point of my reactive power compensators? Those will not be able to do with the DC-OPF. We will see another techniques for that, where we'll use other forms of linearization that captures all the properties of the grid here. But the DC-OPF gives a first global problem, a global solution to the problem. That's something very common when you have non-convex problem. If you have to solve a complicated non-convex optimization problem, you will typically always do it in 2 steps. First, the second step will be an optimizer that's able to find a solution that is not too far from a given initial solution. So, because if your problem is non-convex, there's not much you can do, but one thing that works well is to find the optimal solution that's close to a given initial operating point. How do you find a given initial operating point? That's the first step of any solution method, of many solution methods for non-convex problems. Well, you're trying to find a heuristic to find an approximate solution of your problem. DC-OPF is one. So as a first step to solve your problem, for example, should you shut down a gas power plant in Germany or not? So that will generate 500 megawatts. So that's a big decision you need to take. So this decision you will take using DC-OPF. Then, in order to know exactly what would be the voltage and what are secondary actions you will need to take to control the grid, then you will use local optimization that we will see later. So now to the DC-OPF. Having simplified so dramatically the grid, we have simply replaced all the constraints by the linear constraint that I said before. Now, if you have an objective function that is convex in P, the active power, then this set of constraints gives linear constraints, and we will have a convex problem. If the objective is linear, we even have a linear problem here. In the toy example we had a few minutes ago, the objective was linear. So the injected power is the G here, and the costs are simply proportional to the power, so fixed cost here. So I can solve this. I can write these equations, and I have the equations I'm writing here. Here I'm writing the power injection at node 1, which is active power only. That's the difference G1 minus L1. And here, this is the power flow that is exiting node 1. That's the power that's flowing on line 1, 2, because theta 1 is 0, I have only minus theta 2, and this is what is flowing on line 1, 3. I have two other lines, 2, 3, etc. Here I've added power balance, that in some sense, as we saw before, is redundant. And then I have also that the injected power on the power on line 1, 2 is given by this. That's the sum that we saw. That's the basic formula we saw before. And here, the only way I'm able to capture the line constraints is by saying the apparent power must be limited here. So that gives here, in this case, a completely linear problem. I solve it here, and with the same value that I had before, I find, of course, a slightly different problem, but as you will see, it still gives qualitatively and up to a few percent the same thing as before. So we find that when the line constraints are, as we said here, the most power, the saturated generator is generator 1, and power is flowing from 1 to 2 and from 2 to 3. And the line that is saturated is line 2, 3. We see that here with the capacity, and that is full. The marginal costs will be slightly different, but they will not be very different from what we had before. And we find the same thing similar here, that if I increase the line capacities by a factor 10, then the generator that is operating at full capacity is generator 2, and we see also how the marginal costs are evolving. In this thing here, we find that the marginal cost at all nodes is the same, which is a symptom of two things. First, we have a grid that is completely transparent. It has such a large capacity that it doesn't matter that it is as if there was no grid. It's called a copper plate. Everybody is connected to everyone without any constraints. So in such a case, the marginal cost of operation is the cost of the generator that is of lowest price among all the generators that are not saturated. I have 3 generators here. This one is generating at full capacity, is the cheapest. This one is the second one, and it is not saturated. This is the third one. So the marginal cost is, if we want to increase consumption, we will ask this one to produce more, and the price will be 15. Same for all. Again, the same for all is a symptom of the fact that the grid is non-limiting.
Sorry.
In the lab, you will do other examples where you will see that the marginal cost can take more complicated values. One question?
Yeah, sorry. In the last slide before, when you compute the marginal costs, you don't use the LP, right? You use something else.
No, here is the cost used within the DC solution. So it's used with the LP, yes.
What is it exactly in the LP? Can you just say what is it exactly in the LP, please?
Well, this program. This is a linear program. So I'm solving here the OPF with the DC approximation. That means what I have approximated are the constraints of the grid. And because my cost is linear, my constraints are linear. This is a linear optimization problem, called a linear program. So within this context, assuming this approximation, those are the approximated marginal costs if the DC approximation would be correct, would be not an approximation, but the true thing here. Right? So we find that the marginal costs are sometimes difficult to interpret. Here it's easy to interpret because this generator is saturated here. It's running 400 megawatt full. This generator is not saturated, so the marginal cost here is the local cost. That's easy to understand. But why this cost is higher here has to do with the power flow. If I add 1 megawatt of consumption here, because this one was saturated, I need to, this thing that was produced here will need to be produced by a mix of this one and this one. And this mix gives this cost that is given here. Why a mix? Well, because even with the DC approximation is capturing how power flows as with a fairly good approximation. And as we said before, I cannot decide to send some power here and assume this would have no side effect on the rest here. So if I'm sending power, if I'm increasing power will flow based on the resulting voltage angles, not because I decided to send power to one place or the other. We'll talk more, we'll discuss more about marginal costs in a few more points here. If we do unit commitment, if we add ramping constraints, and also the decision whether we switch on or not a given generator. If we do this, then we no longer have a convex problem, not a linear problem, of course, because we have binary variables. Here, the binary variables are the WI, where I say whether a certain device is on or off. And typically here, there are startup costs and start down costs. If you stop a unit, that costs something. If you start it, that costs something, regardless of the running cost that will be present during the next period. And that transforms the problem into a problem that has both linear and integer part. So we have a non-convex problem, which in general is complex, but among the non-convex problems, the integer linear problems are the ones that can be best solved. So there are relatively efficient solvers, which for problems that are of sizes not too large are able to solve it here. So this is typically what would be done for a dispatch plan. Having integer constraints with a true OPF problem probably in most cases breaks all complexity. So even there, we're happy to have the DC approximation to do this. Voilà. So more on this is in the labs. Before moving there, a few questions to check your understanding of the DC approximation. Here, I'm proposing a number of assumptions, 3 assumptions A, B, C. Which of these assumptions are true? I'll close the poll in a few seconds. And the majority says D, which is, of course, correct. Line resistance are taken to 0 and voltage magnitudes are set to 1. Of course, if you set also voltages angle to 0, then you don't get anything. So it is an approximation that is trying to capture exactly the voltage angles, because in high voltage grids, the voltage angles at first order are what determines the power flows. 3 more assumptions. Branch power flows have equal magnitudes in both directions. There is no power loss in the branches. And the DC approximation is called this way because it models a DC grid power flow. I close the poll in a few seconds. Closing. Branch power flows have equal magnitude in both directions. This is true. This is true. There is no power loss in the branches. This is true, nor anywhere, by the way. The losses are always in the branches. And is it called this way because it's a DC grid power flow? Unfortunately not. And so this is a misleading terminology. That's perhaps it's useful to know why. But because of something else, the power flow equations in a DC grid are quadratic and nonlinear and non-convex. So they are just as nasty as in an AC grid. There are fewer variables in an AC grid. You have complex variables, so 2 complex number per phase, and typically you have 3 phases, so you have 6 complex number per node. In a DC grid, you have only 1, so you divide the number of variables by 6. But other than that, it's not easier. But the DC approximation is similar to the laws that relate current to voltage, so the Kirchhoff law in a DC circuit, right? So if you think of current as the replacement for active power and the voltage as the replacement for AC voltage angle, then you have exactly the same mathematics. So you can map one to the other. In that sense, if you want to analyze a DC circuit, when you're speaking currents and not power, then you have exactly the same formalism as the DC approximation of an AC grid. But of course, in an AC grid, I was interested in currents, but in power. That was our first radical approximation, the DC approximation. Another one that is very commonly used, and that's the only other one we will see in this lecture this year, is the linearization of the AC OPF problem. It has a name, it's called voltage sensitivity coefficient. What it is in reality is simply taking the Taylor expansion at first order. So it's the standard linearization we do in nonlinear systems. We linearize the system by taking the derivative. So let me write this. To simplify, I take a single phase grid because 3 phases is really terrible to describe, but essentially it's the same. The power flow equations are given by this equation we saw already. The injected power at a node is given by the complex power at this node times the complex current injection, which is derived from the admittance matrix, and we take the conjugate to obtain the power injection here. So I can write this in complex form with S. S is a vector. All the complex vector injection at all nodes is some function, which is this quadratic function of the quadratic and rectangular coordinate of the complex voltage here. And because it's quadratic, multivariate, this is what makes it a nasty problem here. For example, if we think of the load flow problem, the load flow says if I know the power injections at all nodes, what is the state of the grid? Given the state of the grid, I will be able to compute the voltage magnitude, the line currents, everything I need to know. So that's the inverse problem. Given S, find V here. Right. So assume and you've seen how to solve the load flow with Newton-Raphson. So assume I know a solution that I call V hat for a given S hat. So I know a local solution of my grid. Why do I know that? For example, because this is a first operating point. So everything we're saying in this part is local linearization. We're doing approximations of the AC OPF that are true as long as we remain close to a given operating point. Now, as you know, if we know V hat and S hat, so S hat is F of V hat, I can approximate the function V by its first order approximation, which is the value at point V hat, which is S hat. This notation here is called the Jacobian matrix. It's also called the differential. It's the differential of the function F. It's an n by n matrix. If n is the number of components of V, which n is not the same n here, is the total number of rectangular coordinates. And this dot here means the product of this square matrix by this vector here. which is the delta of the complex voltage, or we can write it in complex coordinates, but most of the time we write it in rectangular coordinates here. So in rectangular coordinates, this is linear. Now, since we have linearized at least some of the equations of the grid, there is a hope that we can transform a power flow into something that is largely linear. Remember, this linearization is only true locally, so this could not be used, for example, to solve global problems like we discussed before. For that, we would use the DC approximation typically. The load flow Jacobian matrix that I mentioned is very often used in polar coordinates for the grid state, for the complex voltage, and rectangular coordinates for the power, because we're interested in active and reactive power, and we're interested in voltage magnitude more than the active or the imaginary or real parts of power do not have any real interesting physical interpretation. So if we put it in this form, we have a different mapping f. It's a change of coordinates, so the function f, we're expressing the same thing, but the mathematical formulation we'll have is different. And this is the one that is very often used here. In the Jacobian matrix of this, I write it now explicitly. Typically, we need to decide whether we put all the v's and all the theta together or per node. There's various conventions. Here I'm putting all the active and reactive and all v's and theta, and that gives me the Jacobian matrix, typically called J, and you probably have used this in some form or other when you were using numerical solution with Newton-Raphson of the load flow problem here. So that's the matrix of all derivatives, and you can obtain it, for example, with a load flow solver, if you don't want to compute it here. How can you use this? Well, let me give a canonical example, voltage control. Assume we have potential voltage problem in a grid. In the past years, voltage problems could occur because of overconsumption. But now we have problems because of solar panel. So solar panels are generating power. If you generate power, you increase the voltage typically. So you may have over voltage problem. So you may do some things against the over voltage, but the problem is that the solar panel are not something constant. They depend on the weather. So the voltage fluctuates dramatically. So that is a motivation for introducing voltage control into grids where you have a lot of solar panels. How can we solve voltage control problem? Well, we can do an OPF. Well, the goal of the OPF is not to minimize the consumption, the cost of generators, but to minimize the problems due to voltage. So one way to put it is, for example, to say, I want the voltage magnitude, so little v here is only the magnitude. I want the voltage magnitude to be close to 1. So I want to minimize at all buses, a penalty function, which is the absolute value of the voltage magnitude minus 1 here. You recognize our friend, the absolute value, which gives a convex function, but nonlinear, but we know how to transform it into linear terms. Plus, typically, you will also add, by doing that, you may draw more power, you would change the power flows, and in a grid, for example, if you're controlling a microgrid, then the power that matters is the power that you draw from the slack bus being the main grid, the one that you pay for. The rest, the solar panels or the local generations, are your microgrid operations. So you don't pay for it, or at least you pay the investment cost, but you don't have running costs for that. So you care only about this. So that would be a very typical objective for a voltage control of a microgrid or a distribution network here. How can we solve this? Well, exactly, it's very nasty. Even if we take the absolute value as a trick to transform it into linear things, the power flow equations will make it very nastily. But typically such a grid is not operating in an arbitrary setting. The power flows that are consumed or injected are close to things that can be easily forecast. So we can have a known operating point where the state of the grid, V hat, theta hat, and the power injections, P hat, Q hat, are known here. Perhaps, for example, the forecasted one here. Then we can linearize the problem by saying, I will control the voltage in my grid by transforming my power injections. For example, if I have a lot of solar panel injections, I may consume more in a battery, or I can also inject or consume reactive power to mitigate the voltage problem. How can you consume or inject reactive power? Well, at solar panels inverters, for example, I can change the cos phi, the angle of the power injected by the inverters. That will typically be at a small cost of reducing slightly the active power that's generated, but only very minimally. And that will be taken care of by the other term of the objective function we had that will be compensated by the slack bus. So the linearization that we'll obtain is that if my control variables are the p's that I want to modify here, I can say that the state of my grid can be expressed linearly, as the state is the v's and the theta is a constant, that's an operating point we know here, times a big matrix, which is the inverse of the Jacobian matrix, times this here. This is the matrix that is called the voltage sensitivity coefficient. Why voltage sensitivity? Because it expresses how the voltage magnitude and the voltage angles are affected by a change in the power injections or consumptions of the grids here. And they are typically used now to put in my optimization problem. I have replaced the grid equation by this, which is now completely linear. And my problem will be, for example, to minimize the deviations of all the voltage magnitude from 1. Voila, this is how linearization can be expressed. Time for another break. So we break until 11:15, and after the break, we will try to put that in practice.